Welcome to the first PowerPoint of Chapter 5. Please note that this presentation includes information from Section 1 and Section 3 of Chapter 5 in your textbook. So those of you who are using your book, in addition to the Moodle resources, you will have to skip around a little bit here and there. How have we come to our discussion of electrons after all that time in Chapter 4 talking about protons and neutrons? It is time to talk about the electrons. The men highlighted here in these next two slides were truly on the cutting edge of the two most important components of science. First, a creative mind, representing the ability to dig deeper into existing ideas and then think outside the box and push science into a new direction. And second was the ingenuity to design experiments and construct new technology in order to test their new ideas. Their ideas can be strung along a timeline as in your textbook, but we need to appreciate how these men worked together, with each other, building off of each other's discoveries, in order to build our understanding of the invisible world. Niels Bohr had actually taken experiments dealing with the light produced by heated chemical compounds, observations that had been around for quite a while, and used them to develop an idea for organizing the electrons in the space around the small, dense, positive nucleus. Niels Bohr revived the concept of spectroscopy, studying the emission and absorption spectra of elements, which provided much needed support for what was called the Rutherford-Bohr atomic model. It's the Rutherford model because it has a small dense positive nucleus, and it's the Bohr model because this spectroscopic evidence led to Niels Bohr's organization of the electrons in energy levels around the nucleus. When scientists look at spectra, they see three different kinds of spectra, and these spectra are produced differently because of the source of the light. In this first example up here on the top, if you have for example, a solid metal filament inside of a regular old-fashioned light bulb, that object produces a continuous spectrum when the light from that object is passed through a diffraction grating. A diffraction grating is basically a piece of plastic that has thousands of little ridges in it, and it's a technological advancement that replaces a hunk of glass called a prism that was pretty uncomfortable to carry around in your pocket. In the second kind of spectra, called an emission spectra, a hot gas gives off light, which passes through a diffraction grating, and what you see after analysis are bright lines of color. Very specific bright lines, separated by blackness, the absence of any color. This emission spectrum, also called a bright line spectrum for obvious reasons, is like a fingerprint for the elements. Every element has its own unique signature. And lastly, you have a continuous spectra produced by a hot object that passes through a cool gas before going through the diffraction grating. And what you will see, the kind of spectra you'll see, is an absorption spectra in which certain specific colors of light have been removed from the continuous spectra produced by the hot object. And a sharp chemistry student might see a relationship in this picture that could be worth writing about in your Moodle journal. Well, there are still problems. Well, we don't know what light really is. Well, light is energy. And energy is defined as the ability to do work, like make electrons jump around. Light travels in waves, just like other forms of energy, and waves have measurable wavelengths and frequencies. So it sounds like there's going to be some calculations to do. But Niels Bohr explained that light actually existed as quantized bundles of energy, little packets, each one carrying a different amount of energy. And these bundles of energy were called photons, which sounds like he's talking about particles of light. And that was a very new idea. Well, what are waves? Energy travels in waves, and waves have certain characteristic features that can be measured, and some relationships can be drawn. You have wavelengths, which are the distance from crest to crest of two successive waves, and frequency, which is related to wavelength. The blue waves over here, I think we would all agree, have a higher frequency because the waves are closer together. And the red wave over here has a relatively low frequency compared to the blue wave. Frequency and wavelength are pretty related. Well, how is that? If we take a look at all the different kinds of energy that travels in waves and arrange them according to their wavelength and frequency and the energy involved in producing them, we get a chart called the electromagnetic spectrum. And you have to be careful because different electromagnetic spectrums are organized a little differently. Some of them start, like this one does, with short wavelengths on the left and long wavelengths on the right. You might see them flipped around, and that's okay. You just have to pay very close attention to how you're interpreting this electromagnetic spectrum. You have the long wavelengths on this electromagnetic spectrum are on the right, like radio waves and radar waves, and then a little bit shorter wavelength, you have infrared waves, and they actually produce heat. When they are absorbed by objects, they're almost entirely converted into heat. And then right in the middle, there is this tiny little sliver called visible light, and that is the small portion of the entire electromagnetic spectrum that our eyeballs are actually able to detect. And then you have ultraviolet, which is shorter than the violet colored light we can actually see, and getting shorter wavelengths even still is X-rays, and shorter wavelengths even still is gamma rays. And if you look up above, way at the top, you'll see that energy goes the opposite direction of wavelength. And the shorter the wavelength, the higher the energy, just like we saw in that other graphic. Well, how exactly are wavelength, frequency, and energy related to each other? They are related through the wave equation, through a constant called the speed of light. And the speed of light in a vacuum has a very specific number. It's 2.998 times 10 to the 8th meters per second. In some of your calculations, you'll be allowed to use 3.0 times 10 to the 8th meters per second. Let your calculator do the work you bought it to do, and feel free to use 2.998 times 10 to the 8th meters per second. The wave equation has three variables. Well, it has three components. It has lambda, which is a variable. Lambda is this upside down Y looking thing. It's a lowercase Greek lambda, and it means wavelength. That's the symbol we use for wavelength. It has an F, kind of a swooshy looking F. When Mrs. Gregory, Miss Richard, and I write it on the board, it'll look a little fancier than that, but it's frequency, F for frequency, and the equation is C equals lambda times frequency. And this is what we call a classic inverse relationship, where when one of the two variables decreases, the other variable has to increase. If lambda goes down, frequency must come up in order for the answer to that multiplication problem to be the same, a constant, the speed of light.